I'm Bob Smith, the founder of Demand Peripherals. This video is about our FPGA-based dual quadrature decoder. Let's start with a quick review of quadrature encoding. Quadrature encoding uses two lines, usually called A and B. The relative phase of A and B indicates the direction of travel. For instance, if both are low and A rises first, as shown in this diagram, that might be considered the forward direction. If both are low and B rises first, that might be considered the reverse direction. If possible, you want to use all four edges in the quadrature signals for timing. A common approach is to use A to drive the input of an up-down counter and B to control the direction of the up-down counter. This works and it's fairly inexpensive, but you throw away 3/4 of your timing information by using only the rising edge of A. Whether you're using all four edges or just the rising edge of A, the idea is that you will define a sample period and count those edges during the sample period. You do this for several sample periods, and you compute the frequency as the count divided by the sample period. This works really well if the counts are 100 or 200. It starts to show a little bit of weakness when it's below 50. Below 20 and below 10, you'll really start to expect some problems with your PID loop. Worst case is you might see something like this, where say you wanted to run your samples at 50 hertz, but the input frequency was 75. You'd see a count of 2, a count of 1, a count of 2. The measured frequency then being 100 hertz, 50 hertz, 100 hertz. This would drive your PID loop crazy. There are several common approaches to try to work around this problem. One is to use separate decoder chips. These have the advantage of always using all four edges to do the counts. They also have a slight advantage in that there's typically a shadow register that at the end of a sample period, the counts are latched into a shadow register for sending to the host while the next count cycle starts. You can also use more expensive encoders, of course. If you were using wheel encoders, you could switch to motor encoders. If you were using a magnetic motor encoder, you could switch to an optical motor encoder. Another common approach is to just change the reduction ratio on the gear train. So for instance, if you had 100 revolutions per wheel revolution, then you might switch to a motor that has 400 revolutions per wheel revolution. This, of course, limits the higher speed of the robot, and it makes a little bit more noise. And of course, you could always just live with it. If you wanted to run your PID loop at 50 hertz, well, maybe run it at 5 hertz. At Demand Peripherals, we took a look at this from a slightly different perspective. We've got an FPGA, so we're not limited to the counters available or the hardware that's available off the shelf. We can implement our own. We looked at this and we noticed that from the last edge to the last edge, in this case, say from the first sample to the second sample, that time, we can look at it and see that it's 13,000 microseconds. Let's look at the last edge of the second period to the last edge of the third period, and we see that that time is 26,000 microseconds. So what we did was we added an extra set of counters to count the number of microseconds from the last edge to the last edge. So our frequency is the count divided by the last edge to last edge time, and the measured frequency, as we can see here, would be a consistent 75 hertz. This is what you want to present to your PID loop. All this looks good on a slideshow like this, but does it work in the real world? Let's switch now to a lab setup where we'll measure the performance of our dual quadrature decoders. In the lab setup, necessarily, we'll have to work with the actual FPGA board and the API that drives the FPGA board and the software, the Linux software that drives that. So you'll see the whole system, not just the dual quadrature decoder. Let's switch now to the lab and take a look. Our test bed consists of a function generator, a circuit to convert the square wave from the function generator into the AB quadrature signals, a circuit to convert the 5 volts from the first circuit into 3.3 volts needed by the FPGA, and then a single board computer to run DP-Daemon and provide the API to our application. Let's rearrange the screen a little bit, open up 2X terminals so we can deal directly with DP-Daemon. Start DP-Daemon with the command DP-Daemon. Normally we started with the -L option to specify the binary file to load into the FPGA. This is the command you would put in your rc.local file. The API is ASCII text over a telnet connection, or a TCP connection, but let's use telnet to represent what your application would see. The commands that you're going to use in your application will be dpset to set a parameter, dpget to read a parameter, and dpcat to subscribe to a sensor data stream. So let's set the sample period for the Quad 2 decoder that's loaded to 10 milliseconds. We do that with dpset Quad 2 update period 10. The command line interpreter in DP-Daemon will respond with a / to indicate that it's ready for a new command. Your application should always look for this /. We can now subscribe to the data stream that's being presented by the Quadrature 2 decoder. In this case, we have modified the Quad 2 file so that instead of presenting the count and period for Quad 1 and then the count and period for Quad 2, we're presenting instead the count and period for Quad 1 followed by a division of the count divided by the period, and we present that as a frequency in a scientific notation. We can see here that the frequency is a little less than 3 kilohertz. The maximum frequency for the Quad 2 is 3 megahertz. So let's step up to 3 megahertz and see what we get. And sure enough, we see that we're right now right around 3.0 megahertz. Let's step down a decade at a time. We've now stepped down to the point that there are fewer transitions on the input than our sample update period. So let's go ahead and change our update period to something that now captures that. One of the nice things about DP-Daemon is that the idea of opening a TCP connection and sending commands down it, those commands could also be implemented as shell commands. So what we have is the command dpset Quad 2 update period, and we're going to set it to 50 milliseconds. And now we see that we're we're back to where we have at least one input per sample period. The DP set command from the command line, all it does is it opens up a TCP connection to localhost 8870, copies down all of the parameters, waits for the backslash, and then returns to the command prompt. You'll find that being able to manipulate, view, and test your system from a bash prompt is just invaluable. The other thing to note right now is take a look at the count. The count is going between 1 and 2, which would drive your PID loop insane, but the actual frequency is pretty constant. This is the kind of thing that you really want in a sophisticated robot. The other thing to note, as we mentioned, is the word subscribe. All of the sensors implement a publish-subscribe system. And if you've ever dealt with D-Bus or low-level ROS, you'll appreciate the idea of lines of ASCII text over a TCP connection. And sure enough, we can do that from the command line as well. So dp cat quad2 counts. I say count. The idea of having multiple subscribers makes it easy so that if you want to have one process or thread do motor speed control, you can have a entirely separate processor thread do navigation based on these quadrature readings. Let's do a quick summary and take a look at how much it costs to implement this on an FPGA. Let's review what we've seen so far. We'll also take a look at how to generate dpcore.bin and how you can get a copy of the FPGA card. The Quad 2 dual quadrature decoder uses all 4 edges of the quadrature signal. This gives you the best possible timing resolution. There's no need for the host to poll the peripheral. We use ping-pong counters, and at each edge of the update period, we'll switch from one set of counters to the other. While one is being incremented by the quadrature signal, the other one is being sent up to the host. The FPGA talks to the host computer over a USB serial link, which is full duplex. So we don't have to wait for the host to ask for the data. We can just build a packet of data, put it in the transmit buffer, and send it straight up to the host. Using ping-pong counters also means that the sample period is crystal controlled. It switches on a 40 nanosecond edge from one set of counters to the other. As noted, we count both the edges and we measure the number of microseconds from the last edge to the last edge. This is what gives us really great resolution at low tick rates. If you look at the FPGA cost, it's about 90 cents. That's based on a digit key quantity 1 price. Here we're looking at having 8 dual quadrature decoders in the FPGA, or a total of about 16 quadrature decoders. While it's true that we use an FPGA, no Verilog is required. That's what Demand Peripherals does. You can use Verilog if you want. We provide the source code, but you don't have to have it. How that works is that you would go to our website and the peripherals section on the website. There you will find about 25 different FPGA-based peripherals. Some require special hardware, some, like Quad 2, just need 4 pins on the FPGA. Select 8 peripherals from that list and then go to Support, where you can build an FPGA image. You can use 8 different peripherals or have 8 of the same peripheral. The FPGA doesn't care. Once you hit Submit and give us your email address, we'll generate dpcore.bin for you and mail it to you. Now you're all set. You can run dpdaemon-l dpcore.bin and load it into the FPGA card. Nowhere in this process did you have to build the FPGA image, and nowhere did you have to know Verilog. Of course, the Verilog is available. You can visit our GitHub repository where you will find schematics, the Linux software, and all of the Verilog for all of the peripherals. You can also visit our store where you can buy an FPGA card. Something to note is that for a limited time, we'll give you the FPGA card for free if you buy $50 worth of accessories or interface cards. At checkout, use the checkout code HBRC to get the free FPGA card. I'm Bob Smith, the founder of Demand Peripherals. Thanks for watching.